At places like MIT, a strict line divides the study of pure physics from the practice of engineering. Take a deceptively simple question. If you connect a battery to a light bulb, what is the exact current running through the filament? The absolute physical truth governing that glowing wire is found in the laws of electromagnetism, formalized by James Clerk Maxwell. To find the current using raw physics, you must account for the 3D geometry of the twisted wire, track the heat dissipating into the glass, and solve dense vector calculus across every point in the system. Applying these laws to every component in a circuit makes building functional technology at scale mathematically impossible. To move forward, engineers require a method of simplification. Engineering is the purposeful use of science, achieved by intentionally hiding physical complexity behind layers of logic. We start with an abstraction stack, compressing raw physical reality into a manageable layer. Above Maxwell's bedrock, we stack lunked circuits. These create amplifiers, providing signals for digital logic. From these gates, we build instruction sets, allowing for complex operating systems like Linux. Every piece of modern software operates on the assumption that these underlying layers will discard the chaos of physics and behave according to their simplified mathematical models. To mathematically justify replacing complex physics with simple algebra, we use a technique already familiar to most students. Consider the problem of calculating the acceleration of an object pushed by a force. Introductory physics ignores its temperature, color, and exact jagged shape. The entire entity is distilled into a single property, its mass. This is point mass discretization. By treating the object as a geometric point, we can solve for acceleration using the simple algebra of F equals ma. System design requires this strategic removal of irrelevant physical data to remain functional. We apply an electrical equivalent of the point mass rule to the light bulb filament by drawing a strict boundary around it. This boundary is the foundation of the lumped matter discipline. Maxwell's surface integral defines how charge moves through a boundary. To simplify this, we dictate that the rate of change of charge over time inside this box must be exactly zero. By forbidding charge from building up inside the boundary, the complex derivative term on the right vanishes. This leaves a system where the current entering the box must equal the current exiting. We can now describe the flow of electricity with a single variable, I. By mathematically removing charge buildup, we define a discrete current for the entire component without using vector calculus. To complete the model, we must address the magnetic fields described in Maxwell's equations. The second constraint of our discipline mandates that the rate of change of magnetic flux outside the element is zero. This removes the spatial path dependencies from our math, as the magnetic field no longer influences the electric field in the surrounding space. This assumption allows us to define a unique voltage drop across the component's terminals. With these constraints, the physical object inside the box, whether a twisted bulb or a straight wire, is treated as a discrete schematic symbol, the lumped element. Disciplining nature's variables to zero converts a physical object into a purely mathematical unit. This coordinate plane allows us to categorize components. Because voltage and current are now strictly defined, we can identify any element by the interaction between these two numbers. A resistor exhibits a linear relationship, where voltage is directly proportional to current. An ideal battery behaves differently, maintaining a specific voltage regardless of how much current is drawn from it. When a battery fails, it introduces internal resistance, which we model by tilting that vertical line at an angle. The diode remains off until a specific voltage threshold is reached, at which point it begins to conduct current. To an engineer, the chemistry of the battery or the quantum mechanics of the diode are secondary to the geometry of these curves. The final proof of the lumped matter discipline occurs when we connect these discrete elements into a closed loop. As we travel around this circuit, we determine exactly what happens to the voltages. Returning to Maxwell's line integral, our rules state the changing magnetic flux is zero. This forces the calculus integral to break into simple addition. This is the derivation of Kirchhoff's voltage law. The sum of the voltages in a loop is zero. We have successfully escaped vector calculus and entered the realm of basic algebra. Engineering models are functional simplifications that only provide accurate predictions within their intended physical ranges. If we take a standard lumped element and apply a voltage that exceeds its physical limits, the model begins to fail. While the mathematical model of a resistor predicts a continuous increase in current, the actual physical result is heat, smoke, and structural failure. For example, it is possible to mathematically model a common pickle as a lumped resistor. Pumping 110 volts of AC through that pickle forces the system outside the lumped matter discipline, and raw physics takes over. Engineering is the art of building these mathematical models, while maintaining a precise understanding of where the math ends and reality begins.